To start with the first seminar of our workshop, I think I'd say good afternoon, everybody, again. We're going to start with the first seminar, which is by Professor Herdeiro. I will only say a few words because I think Crispino did a much better job than myself doing that. Professor Herdeiro, as you know, is one of the leading experts in gravitation, I'd say, in the whole world, right? And he's so basically he has more than 200 publications I saw, and I think it's almost 300 right now, so not published, and so this is a really amazing number, and he's gonna talk for us about compact objects with bosonic fields in GR. So Professor.
Okay, so hi everyone. Thank you very much for the very nice introduction, and I will not extend myself too much in the acknowledgements and thank you because we've already had an opening session but anyway, thank you very much to all that contributed to this workshop once again, mainly my good friend Professor Crispino, and I hope that this is not the last. We'll have at least maybe get to 90 will be a bit too much, but but maybe another 9. Well, I think that's a doable goal. Okay, so today I'll talk about compact objects with bosonic fields in GR. This is kind of a little overview talk based on work that I've done throughout the years with many collaborators, some of which are here, and I apologize to the ones that are not. I also apologize because I'm not going to be extensive with references. I mean, there's much related work that I will not mention, and I'll be biased towards my own work. I think that's kind of to be expected, but anyway, I would like to start by telling you the following, if this works. Oh, I think I have to change it here. So we think about many things in terms of paradigms. Paradigms gives us a structure to build concepts and the visualization of the world in many ways. But paradigms also make us develop a sort of a tunnel vision syndrome, because precisely our kind of conceptualization of some topic is based, but also biased by paradigms. And if we think about the particular thing of compact objects, when we do our first general relativity course, of course, we learn about black holes in Einstein-Maxwell theory. That's for a very good reason. This is a very nice model in which the basic black hole solutions are quite simple. Geometry is known in closed analytic form. In fact, the model with enough symmetry is an integrable model. It's a nonlinear sigma model. And there's many solution generating techniques which you can use to get a lot of very interesting geometries. Also, the model does not have solitons in the sense of horizonless, stationary, asymptotically flat, everywhere regular kind of lumps of energy. This was an idea that was proposed a long time ago that perhaps they could exist, but they don't exist in Einstein-Maxwell, although there are some limitations in the current proofs. The black holes that exist and that are textbook material, they are simple enough, meaning that they are described by a small number of macroscopic parameters, and people talk about them as having no hair. There's some uniqueness theorems, only perhaps 2 astrophysically relevant parameters, mass and charge. There can also be electric and magnetic charge. People think this is not so relevant in terms of astrophysics. And perhaps a more academic aspect is, well, if you consider no kind of electromagnetic interactions, but just gravity, relativistic gravity has more than Newtonian gravity. In particular, it can have some kind of effects which can even be repulsive. You could envisage the possibility that there could be, 2 of these objects in equilibrium. A multi-black hole solution, stationary, that can exist in electrovacuum, the medium, the Papapetro, but in the absence of electric charge, it cannot. And nothing of this really changes if instead of one Maxwell, you have many Maxwell fields. In particular, you can have two, and then you can cast the two Maxwell fields as a complex Maxwell field. But you do something that appears to be a tiny change, and things change dramatically, and that is to add a mass term to the Maxwell field. Then you have Einstein-Maxiv complex, minimally coupled to Einstein. You can call this a complex Proca-Einstein theory. And what you see here is very similar to what happens if instead of the complex Proca field, you have a massive complex Klein-Gordon. You can be free, it doesn't need to have self-interactions, but you can also add self-interactions. And in that case, you know, the downside is mathematical. The mass term is an obstacle to the integrability structure. And the simplest solutions even that have these bosonic fields, the scalar or the Proca excited, they are non-trivial, are numerical. So there are no nice kind of analytic closed form solutions anymore. But the upside is physical. There's now a very rich landscape of lumps of bosonic energy that self-gravitate that makes things very different from electrovacuum. And these are called bosonic stars, and often they lead to some dynamical surprises, and this is one of the aspects I would like to emphasize today. Also related to the existence of these, you can superimpose a kind of nonlinear bound state between a black hole horizon and these sort of bosonic environments, and you can get black holes with hair. And this is also related to the very interesting phenomenon of superradiance. There's actually a very generic, it's called synchronization mechanism that started for asymptotically flat black holes with this paper, which I notice now is 10 years old, which is, wow, we are getting old. And this is a generic mechanism that can allow spinning black holes to be in equilibrium with a bosonic environment. Also, there is an electromagnetic version of that. Instead of a synchronization condition, you have something called a resonant condition. And in fact, there's going to be a talk by Eugene Radu in this conference where he's going to make a kind of a discussion of this and showing that in Kaluza-Klein theory, you can actually relate these two conditions, the synchronization and the resonant, in a very nice way. And related to superradiance, there's going to also be a talk by Louise Late. And superradiance is also interesting in the context of these black holes and, in general, the interaction of massive bosonic fields with horizons. And also, as another point of distinction, with the existence of these bosonic fields, you can balance neutral black holes asymptotically flat and without, you know, any pathologies like conical singularities. And this is a construction that we've shown last year together with Eugene. You can have two spinning black holes balanced by their synchronized hair, which is, of course, a very fine-tuned system, but it shows that in some circumstances you could have the scalar, or in this case, but also vector interaction to actually counterbalance gravity and even overcome it, which could be interesting even in dynamical systems. And related to that, there's going to be a talk, I think, by Caio Macedo, in which he's going to be talking about the binaries in these bosonic environments related with dark matter, to which this may or may not have some relevance. So, but today I want to focus on this landscape of solitons in the simplest case, because that's a construction that can be extended in many different directions, and this would not be doable to do a review of all of that in a talk. So that's the, my first goal here. And I would like also to advertise that these bosonic stars I'm going to be describing are often described as echoes, exotic compact objects, and there's going to be a course related with this by Guilherme Raposo, and I'm not sure what he's going to be talking about and if I'm going to cover some of what he's going to be saying. And also Gonzalo has a talk on 2+1 dimensional exotic compact objects, so there might be some relation there, but I don't actually know what he's going to be talking about. But anyway, I take the chance to advertise it. Okay, let me start with something basic, which you've probably heard from me. These bosonic stars have a macroscopic perspective, which is that they are described by this field theory, an effective field theory perhaps, minimal coupled to general relativity, They are very physically reasonable matter sources. Complex massive scalar fields or vector fields. You can have self-interactions. They are not mandatory. In some cases, they are pathological. You have to be careful. Some cases, they actually mitigate problems. Some cases, they introduce problems. So you have a lot of interesting features. And the simplest thing you could do is this. And this is really, really simple if you think about it. I mean, it's just GR minimally coupled to something which is a complex massive scalar field or a complex massive vector field. This is what I'm calling reference models. They always introduce new scale, which you can think this mass can be thought of as a new scale, say in terms of its Compton wavelength, which is associated to this mass, which defines where things can be most interesting. And as I've said, these are my reference models. And then if you kind of have been working on this, or if you know about this, you kind of understand that, well, there are these lumps of energy, they are self-gravitating, both in the case of scalar and in the case of vectors. The simplest solutions are static, and there are also some spinning solutions. So in the static case, you have something that you can call a monopolar solution. It's just a spherical star. Actually, it comes in a family of them because there's a countable number of solutions depending on the number of nodes. That is, the bosonic field, the scalar field, or some component of the Broca field can intersect the axis. And there are solutions where there are no intersections, or you can have a certain number of intersections. And these are somehow similar to the 1s, 2s, 3s orbitals in hydrogen. They are spherical, but they have a number of nodes in the wave function, the radial wave function. But you think, well, this is the most kind of basic structure. Perhaps, well, this should be the kind of the fundamental state, especially if there are no nodes. But you can also build more complicated structures, and that's already very against the spirit of, the simplicity of black holes. These can be fairly compact objects as well. They don't have a horizon. You can have multipolar solutions, and I'm going to be discussing something more about these. So the simplest one is the dipole. So there's a kind of a dipolar structures. In the scalar case, you can think about this as two of these scalar boson stars, which are kind of in equilibrium, and they are balanced because of some repulsion due to the scalar field. In the vector case, it turns out that these dipolar solutions are kind of prolate spheroids. And you think, well, these are kind of excited states, like your p orbitals in hydrogen. But it turns out that dynamics tells you that it's not quite so. In fact, in the scalar case, your expectation was kind of right. This seems to be the fundamental state. It's dynamically robust. But in the vector case, the dipolar solution turns out to be preferred dynamically to the monopolar one. And I'm going to be telling you more about that. And you can also give spin to these things. And when you have the scalar solutions, the simplest spinning solutions turn out to have this kind of energy distribution. They are a mass torus in general relativity. They are toroidal in terms of their morphology, not topology of the space-time. The topology is trivial, but the morphology of constant energy density surfaces looks like that. And whereas in the vector case, there are these spheroidal kind of objects, which is like the spinning Earth. But again, dynamics is quite different. The spinning scalar stars are not able to retain their angular momentum, at least in the simplest models, and either they kind of want to get rid of it, or they want to decay into a black hole if they retain some of the angular momentum. Whereas the vector case, these spheroidal stars seem to be dynamically robust. So this is kind of to give you a flavor that there are some very interesting dynamical distinctions about these things. Now, if these things are realized, you might want to go a little bit beyond and think about, so what's the origin of these new fields and so on. And this is related to a more microscopic perspective of these bosonic stars. So people talk about them often as a Bose-Einstein condensate in which you have many ultralight particles in the same quantum state. And the need for ultralightness comes from, if you'd like these stars to have masses in the astrophysical mass range of black holes, then you will need this, because of the way at least in the simplest models, the maximal mass of the stars scales with the mass of the scalar or vector field, then you need this vector field or scalar field, let's call it fundamental quanta, to be in a mass range which, from the viewpoint of particle physics, are very much ultralight particles. So 10 to the minus 10 to 10 to the minus 20 electron volts in order to have this maximal mass from 1 to 10 to the 10 solar masses, which is roughly where we have evidence for astrophysical black holes. And of course, this connection comes from the wish or the attempt to make these objects be black hole foils. So to actually ask the extent to which the phenomenology of these things could imitate that of what we call black hole candidates in astrophysics. So then there's the question, I mean, could you have, from a decent particle physics model, this type of very ultralight particles? And there are various attempts to that, but there is a famous one which comes from string compactifications called the axiverse. There's a very important relation with this fuzzy dark matter. If nothing else, you may want to say that studying this type of stars is related to trying to address one of the fundamental problems that we have in physics, I would say, today, which is that of dark matter. And this ultralight dark matter relates to this fuzzy dark matter. And in terms of high-energy physics models that could give rise to this, there's one other kind of reference here that you cannot see, which is related to simpler extensions of the standard model of particle physics where you can get these type of ultralight particles, typically with some extra baggage, not just this, but that could give you hints of how you could embed these models in particle physics. So let me say a little bit about the stability of these stars, because if you'd like them to be viable candidates for something to exist in the universe, stability is really important, and about the fact that these vector stars, they actually do not have as a fundamental a ground state the spherical stars. So the simplest of these bosonic stars are the spherical models. And when you try to compute them, you basically give an ansatz, a form for your scalar or your vector field that has this harmonic time dependence. This is the way to circumvent Derek-type arguments that don't allow lumps of energy that are stationary otherwise. And the typical space of solutions that you find looks like this. You have on the left the scalar case, on the right the vector case. There is here the frequency, and this you can think as the mass if you look at the red curve. So there's a maximal frequency, which is a condition for the state to be bound. There's a maximal mass, which is the one that I was showing you in the previous slide. And there's a scaling of this maximal mass with the mass mu of the field. So this is the ADM mass of the spacetime. Now, the lesson that one classically gets from the literature when looking at this is the following. There is, by studying radial perturbations, a stable branch of solutions. So the solutions that appear between the maximal frequency to the maximal mass, in either case, they are stable against radial perturbations. The other ones are not beyond this point. And this, first of all, has led to the idea that, indeed, you have here some dynamically robust solutions that are perturbatively stable, and therefore, these are really the ground states of the model. There's also the knowledge of what happens to the non-stable solutions. They can have different fates. So Carolina is actually going to be telling you a little bit about how this is done, this sort of perturbation theory. So in this slide here, I'm just going to advertise her talk and tell you that when you look at these perturbations, This is for the vector case. What you find if you have a perturbation mode with a frequency capital omega is that along here, the capital omega square is positive, so you have something which is stable, but beyond there, then this omega square becomes negative, so it has an imaginary part, and so the mode can grow, meaning that the solutions then are unstable against the spherical perturbation. But, you know, there could be the possibility that the spherical story is not the whole thing. Although it was kind of unlikely, and there were some evolutions, even using, you know, nonlinear evolutions, like in numerical relativity, where things that they seem to be pointing towards the spherical stars in both the scalar and the vector case being really stable. But it turns out that the spherical mini-Broca stars are unstable, but they are unstable against non-spherical perturbations. I thought this was a kind of surprising result. And in order to explain it to you, perhaps it's a good idea to tell you something else that goes along the lines of this multipolar freedom that stars have and black holes don't. And this is a materialization of how this multipolar freedom can happen for stars. So these bosonic stars, and now I'm going to focus on the scalar case, you can have solutions to the full Einstein-Klein-Gordon equations, which are not just a little round thing or a toroidal thing if it's spinning. You can have multipolar solutions, which are in a sense akin to hydrogen orbitals. So here's one way to think about it. You think about the Klein-Gordon equation in flat spacetime with a mass mu. This is something you can solve very easily. There are solutions with this type of ansatz, a harmonic time dependence, a radial function, and there's a spherical harmonic here. And the radial function turns out to be a Bessel function type. This is simple, but there's a problem. The solutions are not regular. They diverge. These ones diverge at the origin. But when you turn on gravity, gravity regularizes these divergences. You can have solutions for any L and M. Here I'm going to be focusing in axisymmetric things, so I'm putting this M to 0. Then you can have solutions with these different L's. And the nonlinear continuation of these solutions gives rise to these multipolar solutions that you see here that can be constructed as exact, well, numerical solutions of the Einstein-Klein-Gordon system. So you can get something that is like a monopole, something that's like a dipole, and so on and so forth. And here's some like quantum numbers that give you an analogy with hydrogen orbitals. Of course, you'd think, okay, these solutions exist, but they are all unstable. And that's probably the case for most of them. But they could be still fairly compact as solutions of the self-gravitating system, and they exist. They don't have a horizon. They are not black holes. They don't violate anything you know. So this would be the monopolar solution, the dipolar solution, the quadrupolar solution. You would think this is like the kind of the ground state that has less energy, perhaps for, you know, the same frequency, this has more energy, and more here, and so on. And this expectation would be right. So this is like the curve of solutions for spherical, dipolar, quadrupolar. And you see indeed that for the same frequency, you would have that there's more ADM mass for the higher multipolar solutions. That was for the scalar case. So you could think, okay, let me do the same for the vector case. Now, for the vector case, it turns out that it's not like that. So the simplest solutions, the monopolar ones, are here denoted in terms of this dashed dotted black line. So it's this one here. The dipolar solutions are this one, the blue solid line, and the quadrupolar, this red solid line. And what you see is that, fixing, say, the frequency here, the energy, meaning the ADM mass of the dipolar solution, is the smallest one. So this is sort of energetic evidence that these solutions look like a ground state. But of course, the true discriminator of what should be, a ground state is, and therefore the most stable configuration, is dynamics. So what we've done was to ask a question. If these dipolar protostars are the ground state, are they stable in a long-term numerical evolution? To test this, what we've done is the following. We've chosen some illustrative solutions, 1, 2, 3, 4. These dipolar that look like these prolate spheroids. And let's put them in a computer and try to evolve them. And if you'd like to know how, then Miguel will explain everything to you in his course on the Einstein Toolkit. So what you see here, these evolutions were actually done by Nico Sanchez-Gual. And here you look at basically the imaginary parts of the scalar Procap potential. So one of the components of the potential, and this is the energy density. You can see here, this is a kind of a prolate type object. And here you see it's a dipole. If you leave them to evolve, they are fairly dynamically robust. You see it's only some phase dynamics, but doesn't seem to happen anything to them. They just stay there. So that corroborates the energetic evidence. They don't seem to evolve into anything else. In particular, they don't want to decay into a spherical solution. Then you ask a second question. So if these dipolar protostars are the ground state, are spherical stars unstable? Could you have two kind of stable states? Or is there something happening if you try to evolve these spherical stars that you naively thought they could be the ground state? Then you do something similar, which is to choose these some illustrative solutions. Here it's this solution 5, 6, 7, and 8. And you try to put them in your computer and evolve them. This is, of course, not something easy, and it relies on an infrastructure that was developed throughout the years by many people in order to do these evolutions with these bosonic fields. But now it's possible. And what you see is something like this. So at some point, indeed, your spherical stars, they cease to be spherical and they acquire some dynamics. So I'll show you again. So not only the spherical star becomes something that looks a bit more prolate, but it gets a kick as well. The kick is related to some ejection of the Procap field. And it seems to be related to a change in parity of the solution, because in terms of the Procap field, there is a change in parity from even parity to odd parity. And this was something transversal to all of the solutions that we've evolved, and we've seen always this behavior. You can try to do very interesting things to check if this is robust. For instance, a lot of evolutions are done imposing some symmetries in your grid to avoid evolving the whole of the space. So you can say the north is equal to the south. If you do that, you seem to be killing this decay channel. But even then, what we've seen, I'm not going to show you a movie, is that the solutions go through a quadrupolar phase in which there is an oscillation not in the north-south, but in the east-west. And they decay into a prolate state in the east-west. So they find a way to actually circumvent the restriction to decay to the energetically more favorable state. But how is this possible, and how was this missed? Because if people even actually showed that these spherical Procap stars could form from gravitational cooling. They started with, a sort of a cloud of spherical Procap field, let it collapse, and a star that looked very much like a spherical Procap star was forming. Yes, but to do that, they've always imposed spherical symmetry. So you have to do it imposing no symmetries whatsoever. And so if you do that, in fact, you realize that the sphericity is lost and the stars want to become something else. And it's very clear, say, from this evolution, that a dipolar structure is forming, here oriented at 45 degrees, which is compatible with the fact that the ground state seems to be these prolate stars. So there's this interesting feature that you have a vector boson star that is stable against spherical perturbations, but seems to be unstable against non-spherical dynamics. There are other interesting systems, actually, in physics, where a spherical configuration decays into non-spherical one. And a famous one is a charge-liquid drop. And this was found by Lord Rayleigh at the end of the 19th century. Beyond a certain charge-to-mass ratio, it is energetically more favorable for the charge drop to actually distort its spherical symmetry into something else. There are probably deeper reasons that we are still unaware of, but this seems to be a robust result. So maybe you were wondering, so what's the impact for the spinning case of these Proca stars? Well, there's a very interesting story here because, well, first of all, when the first Proca stars that were spinning were reported, people didn't get the right fundamental state with spin. They got an excited state. For historical reasons, I'm not going to describe them now. But eventually, what we think are the fundamental rotating Proca stars, they were found. And they seem to be dynamically robust, as I described, and more dynamically robust than their scalar cousins. And this was a work that was done a few years ago. This simulation here was done by Miguel. And this is the evolution of a spinning scalar boson star. So what you see here is, you can think about as this toroidal structure of the star seen from above. And after a while, there's a non-axisymmetric mode that destroys the star, and there's collapse to a curved black hole. So what you see here, there's an apparent horizon form. This instability of the spinning scalar stars in this simplest model without self-interaction is not present in the vector case. In the vector case, the spinning stars, even when they are highly perturbed, like these are two illustrations of that, or here we've started with an excited state. You notice that in the beginning it was a Saturn kind of structure. It was an excited state of a spinning Proca star. What we've seen is that the evolution retains some angular momentum. It doesn't shed it away, number one, and number two, it doesn't create a horizon. It doesn't collapse. So the evidence is that the spinning Proca stars are indeed dynamically more robust in the simplest models than their scalar cousins, although the picture is changed by the introduction of self-interactions. And there's a very complicated, well, there's a more complex story there. So going back to something I've said a little bit ago, although in terms of this landscape of solutions, and I'm just talking here about the simplest model for scalar versus vector, there is a similarity in the landscape of solutions. Their dynamics is quite different. And the models that dynamics actually choose, they seem to be different, I would say, to some extent, with a surprise in the scalar and in the vector case, namely the fact that the fundamental, the ground state for the vector stars want to deviate from spherical symmetry even in staticity. So if you think about Israel's theorem that tells you that, that staticity implies sphericity for black holes, here staticity and stability imply non-sphericity for these vector stars, which is kind of a twist as respect to the paradigm for compact objects that you think about in black holes, of course. All of this can be complicated in many ways. You can introduce self-interactions, and there's many interesting families of solutions. And you can also introduce more fields. And there's a lot of interesting things. And the introduction, say, of more fields can lead to composite objects. For instance, the scalar dipole, it actually is unstable. It wants to decay. But if you introduce in the scalar dipole appropriate monopolar states of a different field, you can stabilize it. And this has been seen in the Newtonian limit, and there's also some works in the relativistic limit. In particular, with the right combination, you can get something called L boson stars, in which Juan Carlos de Gollado is going to be talking to you about, that have their own interesting dynamics. But I will not explain more in detail this slide, but just to say that if you choose, for instance, 3 fields with relative tunings of the amplitudes of the 3 fields, you can go from things like the spinning boson stars to something like a toroidal non-spinning star to something like a dipolar star or an L boson star. And sometimes this requires the different fields to have different frequencies and different amplitudes, and sometimes they have the same frequency, and in the case of the L boson stars, precisely the same amplitudes as well. Right, how am I doing with time? How much time do I have? A lot of time. How many? 15. Okay, so why are you doing this, you ask me? Why are you looking at all of these solutions and this landscape? Why are you doing? Well, we do it because we can, first, no, but that's not what you write in proposal, of course. No, you do it because you think you learned something from it. And one of the interesting things is to extract some phenomenology to investigate the extent to which you can imitate the phenomenology of black holes. And so I would like to give you here a couple of examples of what I call imitation game. And of course, I didn't invent this expression. There's a very nice movie called Imitation Game. So I would like to tell you how these bosonic stars can imitate the state-of-the-art phenomenology and observations that we have about the most compact objects in the universe. I will give you an example about gravitational waves, and then I'll give you an example about imaging, black hole imaging. So let me start with mimicking a gravitational wave. At the moment, there's about, well, from the first 3 observational runs of LIGO Virgo Kagra, and now there's more in the O4. There were about 100 events. Well, some were triggers, but about 90 events, and some with lower significance. There were some very interesting ones. One that was highly debated was GW 190521, because it had very special characteristics. The 2 most massive progenitors, so this was a very short signal at the low end of the frequency range. So it was interpreted as the collision of 2 black holes with very high mass. One of them with about 85 solar masses and another one with about 66 solar masses. So when it was announced, these were the most massive progenitors in any gravitational wave event, hi there too. So, and then there was a little issue because at least one of these was in the so-called pair instability supernova gap. So that's a region in the mass spectrum of black holes where specialists in core collapse say that the black hole could not originate directly from the core collapse of a very massive star. QED effects at that point prevent the collapse, and therefore there's a window in which the theory doesn't favor formation of black holes. Because they are very massive, that means they are big, the wavelengths are big, the frequencies are small, and so you only saw the very end of the merger and then the ring down in the event. That was the interpretation. And the final black hole was considered to be an intermediate mass black hole with about 142 solar masses. So the short nature of the event invited for alternative explanations. And so in this paper here that was published already some time ago, we've tried to see if we could explain this as a merger of protostars, the spinning protostars that are the dynamically robust states that I was describing to you before. And in fact, as I will explain to you, you can, and if you do a Bayesian analysis, there's a slight statistical preference, which you cannot give too much weight to, but it shows you at least the degeneracy is there. So let me explain a little bit what we have done. So first of all, you must get a library of templates of gravitational waves from the collisions of these objects so that you can compare with observations. This is something that's absent for non-Kerr models. It's one of the challenges, but this is difficult. It took a very long time to develop the ones we have, and there's a lot of techniques to actually expand the libraries that one can get from numerical relativity with other approximate techniques, because that's very expensive. So here I'm just making a cartoon of two stars. These are, you can think about them as spinning protostars. They have the same mass and the same frequency. They are at some distance d along, say, the x direction. They could have some transversal velocity in the y direction, but we put it to 0 for reasons that I can explain. That's what we call a head-on collision. If they had velocities, it would be a kind of an evolving, an inspiraling binary. So, and then these things can be put as initial data and collided. You might have noticed that there was a little kind of velocity in the y direction that they were getting, and that's because they are spinning. So there is a dragging of inertial frames. So they actually get some y velocity, even though initially they had none. So the head-on collision actually creates, in this case, not really head-on. And then you create a black hole. And if you have some initial data, that is, you choose your initial protostars, you get some waveform, which here is, for the case, you start with these two. And then you can repeat this by varying your initial data. So then you have, instead of those stars to be that particular star, you have these ones, and you kind of go and you scan your parameter space to get your library of waveforms. You cannot go to too high frequencies, because otherwise the final object is not a black hole. Too high frequencies mean the masses are small and you form another protostar rather than a black hole, and that is not compatible with the event. And these examples were all for equal masses, but we've also looked into unequal mass collisions. In fact, there was a catalog that was built with about 800 waveforms by Nico, and I'm just showing you here what you have in terms of some of the unequal mass, where you have the excitation of some other modes, not just the dominant quadrupolar mode. And this is just to illustrate that for non-Kerr models, you can also start this endeavor of building a library of waveforms that you can use for comparing with data, for parameter estimation, and waveform reconstruction, for injections, for whatever you'd like. So then Juan Calderón Bustillo, who actually also led the Bayesian analysis or participated in for the LIGO collaboration, the analysis of this event, did a similar analysis with this other library of waveforms of these exotic compact objects to compare. And, well, there are some priors, some assumptions that you have to take into account, but the most important message is the following. So when you compare both the best fit and also the kind of statistic likelihood, the Bayesian analysis, this is the Bayes factor, you get a slightly higher factor for the protostar model than for the binary black hole model. This is something that has no statistical, well, this is something that has no very large statistical weight. That is, you cannot take this as saying that one model is much better than the other. But it shows also that the PROCA model for this particular event is not worse than the other. So it's just telling you that there is really the possibility that a very different set of objects can explain the data in an event like this, which is very particular. And that is why for this was possible. But let's assume, just for the sake of it, that indeed this interpretation was right. That indeed these were PROCA stars rather than black holes. Then you can actually determine what is the distribution for your preferred frequency. And then, assuming that the overall mass of the final black hole is, the overall mass is essentially twice the mass of the initial PROCA stars, you can actually determine what is little mu. And so you get a statistical distribution for that little mu, which is the mass of the fundamental PROCA star. And it has some peak at some particular value, which here it's about 8.7 times 10 to the minus 13 electron volts. So if you would have a population study in which this would be corroborated, you would be finding a new particle with this type of analysis. That would be a new dark matter particle from gravitational waves. You would be really converting your gravitational wave detectors into a particle detector and say, well, there's a new boson in nature which will have this mass, and it would be a vector. It would have spin 1. I'm not claiming this is right. I'm just claiming that this shows you how you go from a theoretical construction of an exotic compact object to a comparison with observations and potentially extracting new physics. And you can do this in these models because these bosonic stars are really flexible. There's a few other events that were kind of in the same ballpark and had similar properties. Some were disfavored by this type of analysis. Some were comparable to, in terms of statistical preference, with black holes. But to me, the most important thing is this is showing you how the degeneracy problem is there and how your eventual interpretation of events, say as black holes, may be, you know, also may be a consequence of having no alternative theoretical model sufficiently developed to compare with the observations. And this is really, I would say, an important endeavor for the community. So I will not say more about this, but I'm happy to discuss that with you. Finally, let me address a little bit of the imitation game related to imaging. And here, I think there's going to be a few talks that are related to imaging. Here, I'm going to be using these the stars, bosonic stars without light rings. In the case of light rings, there's potentially a problem. Pedro is going to be talking about that. I think Haroldo, that's going to be talking about nonlinear electrodynamics, is going to be mentioning something about imaging. And I believe, but I'm not sure, but that Sam is also going to be talking about, yes, 3 minutes? 3 minutes. 3 minutes, okay. So, very briefly then, because some of you have seen this, maybe. In the case of black holes, the edge of the shadow theoretically is associated to a set of special orbits, which in the Schwarzschild case are just the light rings, in the Kerr case are these spherical orbits, and in general it's something that has been called fundamental photon orbits. And, but you can get an effective shadow without such light rings as well. And that may be because of the properties of the astrophysical environment around a compact object that doesn't have light rings or a horizon. A very nice example was given a few years back by Olivars et al., where they looked at some model of boson stars. These are spherical boson stars with self-interactions. And they found that there's a very interesting feature, which is that time-like circular orbits, so typically they have an angular frequency that increases as you go inwards. But here in these models, there was a peak for this angular frequency at some radial distance, and then it decreased. And they saw that this feature actually quenched the magnetorotational instability in the accretion disk that was leading to the decay of matter towards the center. Put in other words, you know, the property of geodesics, time-like geodesics in this space-time seemed to create a void in the center where there would be no luminous matter, and therefore, if you're looking at it in the right direction, you would see no light coming from it, and therefore an effective shadow. But it didn't quite match, and moreover, the space-time where they saw this was an unstable space-time. So we noticed that for protostars, spherical protostars, actually you could get this feature in a model, which at the time we thought was stable, because these were the spherical protostars. We thought they were stable, and so we thought that this was a better model than their model. You could get this property of the time-like circular geodesics, and spherical protostars, we thought, were stable, and you could actually get the same size of, for the same mass as a Schwarzschild black hole, the same size of this effective shadow and the shadow of the Schwarzschild black hole. But it turned out that this, I'm not going to explain all the details, but I'm showing you an image. So this would be for an observation which is face on, and this would be the Schwarzschild black hole. There's extra features because of the light ring here. The protostar doesn't have a light ring. There's an accretion disk, and it kind of, there's a cutoff because of this property that I've said. But if you blur the image, then you don't see any of the fine detail features that actually could lead you to distinguish the two of them. And that's because you're looking in the right direction, because if you're looking in the wrong direction, which would be edge on, you see very clearly the differences. But because one, in the Proca case, it's not such a deep potential well, so it's not such a compact object. It doesn't have light rings, in fact. So more recently, we reloaded the imitation game, and we've noticed something that we thought was curious, which is again related to the structure of the time-like geodesics. So for some spinning Proca stars, the counter-rotating time-like orbits on the equatorial plane, they admit bands in which they are stable, and then there's an interval where they are not, and then asymptotically, of course, that should approach Keplerian motion, then they are again. So that allows, if you just very naively think, I will put sort of luminous matter in the region where I have these circular time-like stable orbits, it would allow features that seem very similar to the fine features that are associated to light rings in black holes. There's other works about this imitation game. For instance, there Caio has done some work with João-Luís Rosa and other people that also about Proca stars. And I think I'll just say that there's other approaches. I think it's, especially in the imaging, we know still little, and the errors of the current measurements are such that you cannot rule out many things. But let me just say that what one should do to make this more robust and to see if these features are just artifacts of some naivety is to perform GRMHD simulations on these backgrounds to see how much of these features actually survive if you put some more sophisticated astrophysical physics for the disk and for the matter that is giving rise to the luminosity. And this is something we are trying to do with Hector Olivares. So to conclude, and because I think I ran out of time, no? Sometime 10 minutes ago, no? So bosonic stars illustrate these theoretical possibilities. I didn't emphasize too much this in my talk, that there are dynamically robust black hole imitators, but that manifest themselves only at some scales, and this goes into the question of the universality of the Kerr hypothesis. And then producing detailed phenomenology will constrain the model and the corresponding exotic physics, or in the best case scenario, provide a smoking gun for new physics, and this is what I was trying to illustrate with the other example of gravitational waves. So I couldn't mention all of the talks in this workshop in my other slides, so I've decided to put the remaining ones here just to be fully democratic. So thank you very much. And at least Raphael's talk is related to scalar fields, so I think that it fits very well. So.
So thank you, Carlos, for your very nice talk. So we have time for just one question, and please, a small one. So, so can you, if you can go here for, because we don't have a wireless mic, so.
Okay, so 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 thank you very much for your very nice talk. So my question, I don't know if it's a dummy question, but I was wondering the following. So we have boson stars or another kind of objects that can actually mimic some gravitational waves data, right? So I was thinking what kind of astrophysical experiments we could do to actually ensure that we are actually measuring a black hole or not. So my question is that, so because if you have how to build different objects that can mimic the gravitational wave data, what kind of experiments you can perform to ensure that we're actually measuring a black hole or another object? So.
Thank you very much for your question. I think that's what we are trying to do. So are these experiments like, getting this data from gravitational waves and getting these imaging properties? Now, it will end up being about, some statistics in the case of gravitational wave. For instance, there was this one event. Let's assume you take this seriously and you have even accept this statistical preference. We expect to have not one, but 10 or even 100 in the next few years events similar to GW 0519. So will all of them corroborate this? And of course, your theoretical modeling here was very, how shall I put it, rudimentary, because we were not even doing, in spirals of the Procus stars. We were just doing some head-on collisions. So you have a very reduced library. So you have to increase the quality of the theoretical modeling that you do as well. But the question you're asking is precisely what the community is trying to do. So what's the distinctive feature of a black hole? And the distinctive feature of a black hole is that you don't see it to some extent. It has a horizon. You only see the gravitational effects of it. But then if you have a dark matter star, what are the signatures of a dark matter star? Well, you don't see it. You only see the gravitational effects of it. So we are getting here in a little bit of a conundrum. There are, of course, distinctive features about the black hole, but like Hawking radiation or something, but you don't expect that in an astrophysical context. So it will have to be, okay, it will have to be about more data. But then there's an extra question which complicates matters. Do you believe that all of these objects have to be the same? Or could some of them actually be black holes and some could be something else? Of course, we have Occam's razor, which is, let's decide for the model which explains the most being the simplest. But that doesn't work. Otherwise, we would have one particle in particle physics. It doesn't work. That would be simpler than having all the leptons and all the quarks. So if data mandates that we really have to consider different things, But at the moment, it's still, the beginning of a precision era or sufficiently precision for the data about these things. The Kerr hypothesis is great. Perhaps it's oversimplistic. Let's see. Hopefully, it's still in our lifetime. Thank you.
So let's thank Professor again for his lecture.